Yeah. So, good evening, everybody. Welcome to the September edition of the SLAS General Meeting. My name is Jim Small. I'm the president for the society. We do have a few officers here. Looks like we've got a lot more people on Zoom than we do in-house right at the minute. 1, 2, 3, 4, 5, 6. I can count them both on two hands for here. So not sure if you guys just didn't feel like getting out of the house or what the deal is, but welcome either way.
When you counted on two hands, Jim, how many was that?
10.
Oh, I thought it might have been 14.
Okay. Sure.
Jim. Jim.
Yeah.
People, tonight is the balloon glow at Forest
Right.
Park, and people might be having trouble parking.
Actually, there wasn't any trouble at all when I got here about 5 minutes till 7. There was street parking still available right outside the hall. So if that scared you off, it was unnecessary.
How many coffee drinks do you have tonight?
I'll suck down the whole thing.
Decaf or
Just
regular?
regular. All the decaf guys aren't here tonight. Okay, everybody got the screen there? Sorry. Got a little bit of logistics issues here.
Yeah,
So-
I can see his screen, Jim.
Yeah, okay, very good. All right. So we're in for a treat tonight. This summer, after the MISRO convention, was looking around, and I sort of get on the RASC site once in a while. That's the Royal Astronomical Society of Canada. And they run, Laurie, I guess that's yearly, right?
Yes. Yep.
Yeah, so every year they run a really nice conference, and it's virtual and it's cheap as far as conferences go. And I think I put in the newsletter, suggested for people to visit that, but I'm not saying that the quality of the talks was great, but we got 3 speakers out of the deal. So the next 3 speakers, including tonight, are all from Canada. So Laurie and Kimberly Sebald, is it Sebald?
Sibbald. It's kind of like the Calgary thing. Sibbald.
Sybil, okay. So Laurie and Kimberly Sebald hail from the Calgary area. I'll let you explain farther where it is. And the main reason I dragged him in to speak to us is because his talk was about observing exoplanets from his house, from his telescope. And I'm like, boy, we got some people who really be interested in that. What can you do with a regular home telescope as far as looking at exoplanets are. And so we're going to get the lowdown on that. I'm pretty excited about this because at the Jefferson College Observatory, we're in the process of putting together a grant to get photographic equipment for cameras, et cetera, for our observatory, which has got the 16-inch Meade. And so we're looking at the possibility of maybe doing some of the stuff that Laurie and Kimberly are doing. So I'm really looking forward to this. This should be a great talk. And without further ado, take it away, Laurie.
Thank you.
And I'll stop sharing so you can share.
Okay. Is that working? Let's see. Go.
There you
I've
go.
got a green screen. You can see my home screen there, the
You're up.
title screen. Good.
Yep.
Well, I really want to thank all the organizers, Jim, especially, who took interest in our talk at the RASC meeting, and all the organizers of the St. Louis Astronomical Society. We're extremely excited to be able to present to you tonight. We feel pretty privileged to do that. And we'll talk about exoplanet transit measurements from a background of astrophotography. We're informal people. I just want to make sure that people know they have time for questions at the end. If there's something important that I'm fumbled and missed on, please feel free to interrupt me. And Kimberly's going to definitely chime in here on the imaging part. But what we'd like to do is going to talk about our evolution, our trip into this more scientific endeavor that we started really as more pure art form. And it came really from a rather intense effort to obtain quality deep sky images, given more from an artistic vision of what the sky contains. Now, what I'd like to do with the talk first is outline what got us into this exoplanet hunting exercise, because it's important to understand, both technically and, you know, kind of in terms of what our desires and interests in the hobby were. We didn't just wake up, and I say one afternoon, advisedly, because staying up all night, sometimes that happens, and decide that measuring transit was what we wanted to do. It came really from this deep sky image imaging desire. I'm a technically trained person. I'm a chemical engineer. Really, the entire motivation, though, and drive for this was from Kimberly's passion and expertise for landscape photography, which she expanded into deep sky imaging by going through doing some nightscapes, which we'll show. Now, a lot of people have recently taken up imaging deep space objects and our solar system's planets, and it's a challenging, and I think COVID helped that a lot. I think people were staying at home and doing a lot of stuff on their own. It's a challenging, for those of you who've done it, they know it's a challenging, but it's a fulfilling activity, and it really allows you to really clearly see celestial wonders. And equipment to do this has been improving to the point that incredible technology is now in the hands of citizen astronomers. Now, Kimberly has a full-time career, and she's very busy, and she's in the middle of it. She's got a lot of responsibilities, and she's responsible for a lot of people. I'm kind of proud of it, but she's kind of a big deal, not just to me. But landscape photography has always been a passion of hers, and it's great because it allows her to have that big escape, that diversion from her daytime career. But with that, she's somewhat of a perfectionist, just like with her career when it comes to photography. And here's just an example of some of her nightscape work. Here's a Milky Way image from Grassland, Saskatchewan, which is a very dark site in Canada, one of the darkest sites in Canada, that she took with a modified DSLR. It's just a gorgeous picture. It's an award-winning picture. Now here's another shot she took recently. Kimberly, please chime in here. I've got my little spiel, but you can chime in and talk about some of these. Maybe you want to introduce one?
Sure. This is infrared, so it's another passion of mine is doing infrared photography. And this was one of these driving down the highway at 110 kilometers, 60-ish miles an hour. I looked out the back window and I just yelled to Laurie, stop the car. And he did. He pulled over, and this is what I had seen. It was a perfectly clear day, and you rarely get clear days in the mountains. This was just truly a unique opportunity, and the moon was right there, and it just really worked out well. So this one I always call stop the car.
So like as part of her progression, she's been doing a lot of infrared work. So for this particular one, you see the sky's dark. She uses a fully modified mirrorless camera now, meaning that all the stock sensor filters are removed. Normal cameras have sensor filters. These are removed. Spencer's camera in Utah does this, and they're probably the best in the world at it. She then employs long wavelength filters to allow only the non-visible infrared frequencies to pass. In this case, in this particular picture, I believe it was 830 nanometers and greater. And the effects are quite dramatic for a lot of scenes. It offers a really high contrast and detail that visible frequencies alone don't reveal. I don't know if you add anything to that, Kimberly. I'm going to introduce this one. Neowise 2020 July.
July 2020, when we had Comet Neowise and everybody was out capturing all the different Neowise images. This one I was really lucky to capture. It was right at dusk, which was 11:30 at night in Canada. We're quite northern here. And it was passing through the noctilucent clouds and kind of the rainbow of the sunset. It was just a perfect scene, and I was able to capture it.
You can see it's a single 2-second untracked shot, 200 millimeter lens at f2.8 with an ISO of 1250 and with a Canon EOS R fully modified camera. That's a gorgeous shot. Okay, anyway, the initial motivation for starting astrophotography from us was this 2017 lunar eclipse. We bought our first scope, an 80 millimeter APO refractor, and an entry-level equatorial mount. And the desire was to capture the eclipse with the DSLR. So we went to the Oregon coast, somewhat naively, not considering some of the sky condition possibilities, but luckily the marine cloud layer held off long enough to allow us to get some good shots of the total eclipse. And Kimberly processed those. Now from there, the desire to do some deep sky work with the DSLR occurred. First with a stock DSLR and later with a fully modified unit. And that fully modified unit allows deeper capture of reds and slightly beyond. This is an image of the Trifid we did. I think we did this one from Utah. Yeah, it's at Utah. With Kimberly's processing, bringing out the detail. She was using just Photoshop at the time, but now she uses both PixInsight and Photoshop for her processing workflow. After using DSLRs, we wanted to try dedicated CMOS astrophotography cameras. So we got one. It was a so-called one-shot color version with the same kind of RGB red, green, blue Bayer matrix as a DSLR. So in addition, the addition of cooling in these cameras allows much lower noise and therefore higher signal to noise ratio. The picture Kimberly with all her gear processing in her spare time. She's in a tent here because we were in Tanzania at the time in early 2019. We took that trip mainly for photography of landscapes and animals, and it was exciting and successful. But I packed away that 80mm APO and a small travel equatorial mount. And the challenges were pretty great for the astrophotographer, not the least of which was, well, lions and things like that, and I had to get Maasai warriors to protect me. Polar aligning at 3 degrees south of the equator was no fun, but we managed to do it. Just to show you, like, the star trail pictures taken with just a normal camera, but it just shows you what star trails look like close to the equator, and it's fascinating. They don't have that big circular pattern like we do at higher or lower latitudes, higher northern or southern latitudes. So the payoff at that time was really kind of our first decent image with the CMOS camera, and it's a stacked image of the Carina Nebula. Here, the H alpha filter version. It's an incredible sight. It's 4 times larger than Orion. Really, it's a southern hemisphere target, but we managed to get it relatively low, about an hour's worth of exposure. And really, from this moment on, we were hooked into deep space imaging as a pastime. I don't know if you really want to add to that.
Oh, absolutely. This drove the passion deeper.
Now, the background image for the presentation slides is probably really one of my favorite images, if not the favorite that Kimberly processed. Here we're using a monochrome CMOS cooled camera now, so no Bayer matrix filter, and we're using narrowband filters. So hydrogen alpha, oxygen 3, and sulfur 2. For those not familiar, narrowband in this sense refers to light filters that only allow narrow bands of wavelengths corresponding to deep space emission light to pass. And the cooled CMOS camera allows high signal to noise images to be made. And the final product in this case uses the so-called Hubble palette, where the red, green, blue colors are mapped to the 3 different filters. This is a starless version that shows the nebulosity details very well. The image is made up of many hours worth of 20-minute individual exposures. I'm assuming everybody can hear me well. Please tell me if I'm not speaking loud enough.
Oh, you're fine.
Okay, so really, consumer available mount technology allows a telescope to stay targeted precisely with these equatorial mounts, stay targeted precisely at a point in the sky. Now, for imagers, it could be a beautiful nebula, a star cluster, or a planet in our solar system. And in terms of telescopes, whether they're refractors or reflectors, they've continually improved in quality over many decades. And importantly, dedicated astrophotography cameras like the ones we've obtained since, these kind of have, in addition to DSLRs, have improved in their capability to collect those photons of the celestial objects. Now, these are made to work together with mostly inexpensive software that allows image capture using long exposures. Finally, computer control and storage of images is developed with processor and storage speed improvements. Processing of stacked images is developed really to allow hobbyists to create pictures that can rival space telescope quality. Here's a group of like-minded individuals that we know, and with all their equipment waiting for nightfall, and they gathered image together. And up until COVID, we were doing this relatively regularly. It's coming back now, but did this to share knowledge and expertise. It's a very skilled and enthusiastic and talented bunch of people that we know, a group of us here in Alberta. They're a little, and some in Saskatchewan, and a little crazy in that some of the environmental hardships that they're willing to take are a bit extreme. But everybody's passion for the pastime feeds off each other. And really the theme for this is practice in terms of getting good at imaging. And the backyard theme and the camping theme feeds into that. Like really, like all things worthwhile, there's no substitute for practice. It's setting up, polar aligning, getting your craft down. Now, much of the progression in working together was due to the backyard and the camping effort, which allowed us to generate images for process practice as well. Importantly, because of the narrowband imaging, the light pollution in urban and suburban areas can be overcome largely and allow this practice to occur. Now, here's a sub-exposure of 20 minutes duration of NGC 281. This is the Pac-Man Nebula. And this is as it comes right out of the camera. Sorry, was there a question? I didn't hear. There's no stretching or processing of any kind. It's taken using a hydrogen alpha filter of 3 nanometer bandpass. So our efforts have led us to taking long narrowband exposures, which allows processing of detail and more modest total exposure times. There's a lot of discussion about this in the imaging community, whether you should take many shorter exposures or fewer longer. We tend towards the fewer longer. We're not pedantic about it, but that's just that's the style we've chosen and what we do, and the equipment allows that. Now, much of the work was possible, again, from that urban setting in Calgary where we lived. We've since moved to a more rural setting, which we'll talk about in a bit, but this is incredible. In borrelate skies, you can get this kind of image with a hydrogen alpha filter. So these signal to noise ratio is very high. Against this unstretched image. So other filters you take and then combine them and stack them and do a significant amount of processing. So when stacked and processed with the other filters, these images can reveal a high level of contrast and detail of the nebula. And this picture itself of NGC 281 represents 15 hours of total exposure time. And I don't know, probably double that of processing time, right, Kimberly? Something like that.
And we're running about the same. If you do 15 hours on the subs, I'm spending 12 to 15 on the couch processing it.
Yeah. And really, this is where art meets science. Obviously, there's a lot of discussion about this, about pretty pictures versus science, but the features that you see are real, but the art in processing reveals and promotes details and color assignments that the artist seeks. It really is an artistic endeavor at the start, but the features are real features. Here's another narrowed band image. SHO emissions are mapped to RGB with the modified Hubble type palette again, and Kimberly achieves some incredible detail and depth in this image. She seems to have a talent for bringing out a 3D effect in a lot of these nebulas. It was chosen for the cover of this year's Canadian RASC, the Royal Society calendar. Again, okay, so the whole theme of this is showing where we came from to get to this more scientific endeavor of exoplanets. But I give you these images, and we give you these images to give you a feel for what we've been doing prior to attempting those exoplanet measurements and doing some science. The one final image, in talking about the science versus art debate, we both think it's a bit tedious, and we think they're quite complementary, the motivations for doing this kind of work and hobby. And one feeds the other, and the perspective that is gained by placing us in the universe is, I think, the benefit from whichever side you're coming. Here's an LRGB image. It's a non-narrowband image of some dust lanes done from a dark site. We did this one earlier this year. It shows a so-called Herbig-Haro object, originally discovered in '77, which is an ionized gas jet emanating from a pole of a newly formed star in a stellar nursery environment. Again, this image was taken to satisfy our desire, but obviously it reveals a lot more. Okay, that said, it's probably time to talk about exoplanets. Not talking down to anybody. I know people are very familiar with this already from all the things that are out there, but just to be complete, exoplanet transit detection and measurement requires determining the brightness change over time as a usually large Jupiter-sized, say, planet crosses in front of a star that can be around the sun side or sun size or greater, much greater, or a little bit less. This requires multiple exposures, each of sufficient length to allow photons to be captured and counted by the digital camera. Really, all we're doing is counting photons. And my world, photometry really is just a fancy word for that. The incredible thing about all of this is this kind of measurement is quite new. The first type of measurement done like this was in the mid-90s. I guess the first exoplanet was done by the wobble, the redshift method, by a French astronomer, or really his grad student. The guy was on sabbatical. But the actual transit method came a little bit later that, but allowed more prolific work to be done. So the advancements of digital cameras and other equipment being more accessible to more professional people, in addition to, and now in terms of amateurs, allows us now to take part in the effort to adding the data for these. Now, just want to emphasize that all of the demands that good imaging makes sets up for exoplanet work rather well. And all of the tools and techniques that we use in imaging are employed for the exoplanet work. So when we first tried this about 1.5 years or more ago, we didn't know if all the photometry measurements and analysis would work, but we knew that we could image a star stably over a long period of time. In terms of the functions, focusing is basic, but it's much more important to imaging. Indeed, some exoplanet transit seekers intentionally defocus to spread light across more imaging pixels for undersampled stars, allowing them to count the brightness in an equivalent fashion as if they were focused. Guiding, again, it's very important to imaging. Again, for those not familiar, guiding is using the image of a star or stars as a guide to keep the telescope on its celestial target to a high degree of precision. Like small deviations from a stable image are used to provide feedback to the telescope mount for correction. This allows the image to be stationary in the frame. For astroimaging, keeping a stable frame for a long exposure time is critical. Any kind of exposure time is critical. For exoplanet transit, guiding keeps the target star centered in the frame and doesn't wander off, which is very helpful. And the exposure length for narrowband imaging especially exceeds typical exposure requirements for exoplanet transits. For LRGB imaging, it's more similar, but exoplanet work is really no harder in that regard. And framing is key to both. Actually targeting. The development and integration of fast plane solving, which we'll show in a minute, has made this task very efficient for amateurs. So exoplanet transit detection and measurement, the total photon count from a target star, in other words, the star where the anticipated crossing of the planet will occur, as well as comparison stars where no such transits are occurring. Those counts are what is measured and recorded for each exposure. The exposures have to balance obtaining good signal to noise, sufficient data points to define a transit, and keeping a star from moving too much in the image. If you have too long an exposure, you're not getting enough points to define the transit well. Too short an exposure, you might not get enough good signal to noise to get reasonably consistent data. For most purposes, for what we've done, and I think if you look around at some of the databases, typically exposures from 30 seconds, and it's aperture dependent, obviously, and magnitude of star dependent, 30 seconds to 3 or so minutes are typical. Again, a little less than imaging narrowband requirements are used to. And this is just a depiction of the aperture method, with the star, target star, or the other stars contained in a central aperture defined by some number of pixels in diameter. You can see the pixelation. Outside of this is a buffer zone, and then there's a sky annulus reference region that should not contain any light sources, such as small faint stars. Here's an image of a target. It's called TESS Object of Interest 2119. This is one we did, and it's just shown as an illustration of what it looks like on a screen in an image. On close-up, you can see this target star contained in the inner aperture with the sky annulus just inside the fainter star. Pixel definition is evident. This is a 60-second exposure. Again, what we're trying to do is get a count of all the photons we capture that come from the target star, at least as the camera is capable of taking, that has the planet crossing its face, as well as the stable reference stars. This allows a change in brightness, essentially the change in photon count, to be measured as the planet crosses. And the target star brightness measurement is called a relative flux, and it uses the background and reference star brightness measurements to arrive at a calibrated lowering of the brightness of the target star that reveals the planet blocking some of the starlight. Okay, in terms of equipment, we've used a couple of rigs to date. This is our primary imaging scope. It's a 140 millimeter diameter refractor, just over 900 millimeter focal length. Sorry for the units, but we're metric here. It's on the small side for light gathering for exoplanets, but it seems to work well with these mono CMOS cameras, which I'll talk about. All the measurements so far, we've used a clear filter with a UV IR cutoff. So basically, it's a completely clear filter, but blocking the ultraviolet and beyond and the infrared and below. The other scope we've used is a Schmidt acid grain 8-inch reflector. Again, a scope that a lot of people have, and using, again, the mono CMOS cooled camera and a UV IR cut filter. Now, both setups use off-axis guiders, which improves guiding if it's done right. This is the imaging camera here with its cooling function on the optical axis, and perpendicular to that is a guide camera mounted inside an off-axis guide setup that has a small prism that takes a little bit of the light and puts it onto an imaging chip for the guiding function. Now, the main imaging mount, and we also use it for exoplanets, is a Messu 200 Mark II. This is made in the Netherlands by one guy, Lucas Messu. It's a pure friction drive, just metal to metal rollers inside. There's no gears. It's essentially zero backlash. It's an engineering masterpiece, a small observatory quality mount. It does require good balancing, but it's rated for up to 100 kilograms of payload.
Yikes.
It's not consumer pretty, but to this engineer, it's gorgeous, and really also for the cost, it greatly exceeds mounts of its capability. Its capability exceeds greatly mounts of much higher cost. Now, we've used a few different mounts, and the key to them is reliability for imaging. Clear dark sky time is valuable, especially in the warmer months here, which we don't have many of. And so we hate losing exposures to tracking failures and guiding failures. So for imaging, the most important thing is the mount. And this is really true for exoplanet detection also. Tracking failures and guiding failures for exoplanet detection would be disastrous. Amounts of this quality are not strictly required for exoplanet transit measurements, but they help. But more consumer-oriented equipment can also work. And post-processing corrects some errors associated with image alignment in that exoplanet transit measurement area. Now, here's an example for those that are interested of the guiding with the mount. It's shown under good seeing conditions. Here we're imaging, I can tell you, at close to 1 arc second per pixel. So each pixel on the imaging camera represents about 1 arc second of angular deflection. But the guiding is 1/4 of that, which is highly precise. And it makes imaging wonderful, stable images that don't have any star bloat or elongation. But then it's great for exoplanet work. Star movement can be handled through transit measurements that are a little deviation, but this makes it the centering and the stability of the image great. Again, this is another shot back. This is, I don't know if you're doing exoplanet or you're doing narrowband. This is our former situation in Calgary. You can see the suburban setting. We've got lights, condominiums, houses everywhere. But we managed to get those narrowband images there and also start our exoplanet hunting exercise there. Now, in our setup for imaging and also for exoplanet transit, all programs work together, with the hub being a program called APT, so-called Astrophotography tool. It's a Bulgarian program that's very well supported, and it controls or links to everything. Now, there's other programs. There's Nina, of course, and there's, in terms of older programs, there's Sequence Generator Pro, Maxim DL, and there's others. And we're not saying this is the program you need, but this is the one we've used. It's all we can talk about. And we used it from the beginning, and it's been very stable for us, and it seems to interact with the peripheral programs very well. The imaging camera, the settings, the mount, the plate solving, the guider, and the planetarium program all work very well with it. Now, we're using APT because of its excellent stability and its ongoing support. And it really is used in a lot of imagers in Europe. Now, most of the software we use for image gathering is very inexpensive. APT, for example, is 20 euros a year. The rest of the ones shown here, the Stellarium, Planetarium, ASTAT, plate solving, PhD2 guiding, and the ASCOM filter control stuff and mount control stuff, they're all free, which is quite a contrast from some of the hardware and a little ironic in that way. Now, here's a basic workflow for exoplanet transits that we employ. And I'm going to get away from the PowerPoint in a minute and show you just a little bit of this, just to get a feel with a simulated telescope. But it starts with determining a target. And this can be done using some good databases, one of which I'll show you, that contain both established exoplanets as well as candidates. And of course, for people that know about imaging and other work, polar aligning and guide calibration are basic for all imaging and photometry. And I won't get into detail about that, but you need to be able to follow the target precisely, and those functions done right allow that. The essential thing here, it really is simple. The target stays in the same position in the camera frame for the entire duration of the transit, the imaging of that target star. And we compensate for the motion of the Earth under our scope with the mount motion and fine adjustments to it to stay pointing at that same location in the sky. Now, an equatorial mount will allow to do that without any rotation of the image, and that's its great strength. And sometimes we can keep a target star in an image over an entire transit, sometimes within a few pixels. Okay, just quickly, first we take images of the target star well before the expected start of a transit. I'll go over this a bit when I do the demo, but it's just to establish the exposure time that works. Mainly you want to make sure that the light capture does not saturate any pixels that are imaging the star, making the measurement inaccurate. AstroImage-J, the photometry program, is used to process the images. It's the most established publicly available program for doing photometry on variable stars as well as exoplanets. It's not the only one. There's new ones that are likely more user-friendly that are being developed, have been developed. But again, it's the one I started using and taught myself. It's a bit cryptic of a program, but it's very powerful. In many cases, it can be set up so the analysis can be done in real time, which is extremely exciting for me, and I'm sure some of you, the prospect. So you can monitor the transit as it happens, or at least as the light is received here from a few hundred light years away, where it was originally generated. And also, AstroImage-J allows the generation of photometry data reports and transit charts, as well as model results. And we'll talk a bit about data submission and things we've done there in a bit too. Okay, differential photometry calculations calculate the flux or brightness change of the target star. Again, to repeat, this is due to the exoplanet crossing the face of that target star. And the calculation uses reference stars, as we talked about. Once imaging starts, you can wait for all the images to be collected like that and post-process, or you can do it in real time. But just as in astro imaging, calibration frames for the camera are used, so-called flats and darks. Images can be changed during a sequence that can be calibrated on the fly or in post-processing. The basics of a program called AstroImage are outlined in this paper. It's actually a really good paper. It's relatively straightforward, decent language. Math isn't too onerous, and it's worth a look. Again, there's newer tools available too, but they all basically do the same thing. Okay, just a little discussion about, sorry, I just have to move the window here. In all cameras used for exoplanet transit measurements, linearity is an issue. So for photometry work, you want whatever you're doing, whether it's variable stars or exoplanets, you want the brightness or photon count to be measured accurately. This means that the camera digital response must be in proportion to the photons received. This is a linearity measurement of our now exoplanet workhorse camera, cooled to -10. We talked about that 2600 camera, which really is a slightly larger chip. This is just as sensitive a camera. It's a little cheaper. Again, it's a mono. It's a 294 ASI. The cooling features of these cameras minimizes that image noise and maximizes the signal to noise ratio for those star brightness measurements. This example, the measurements I did, it's linear to about 99% of the so-called full well depth of a pixel. As photons are received, they add up in so-called analog to digital units, ADUs. This is a parameter output by the camera as a measure of the brightness of an individual pixel. And summing of these over the pixels containing the star image gives a total brightness of the star. In photometry, if a pixel becomes saturated, such as shown here for high exposure levels, like here in the blue, the counting doesn't take place beyond a certain point. The well is filled. So staying in this linear region is very important. Okay, so we want to stay in the linear region, but importantly, we also want to be able to take images of dim stars with smaller aperture, say citizen type equipment. So low level sensitivity is important. So zooming into the lower part of the scale, you can see what the new cooled CMOS cameras we can use achieve. Again, most of the photometry work is done historically with CCDs. I think the CMOS is a bit of a game changer in terms of sensitivity, but I'm not in a position to say that because I haven't done CCD work, but it's just from what we've done and can present, we're quite excited about the sensitivity. It's the number one reason I think that, along with the other equipment developments, number one reason that citizens can contribute to the ongoing data collection of exoplanet transits, in my humble opinion. I can tell you our setup, and I'll show you an example. The C8 and the 294 camera, we successfully determined exoplanet transit of new candidate exoplanets down to about 5% of the pixel depth capability of the camera. Okay, what I want to do now is wait for the PowerPoint to show some of the workflow adapted from our imaging to exoplanet transit measurements. And really it's an attempt to kind of demystify for people that are mystified, not that they are, but some of the process. And I won't sugarcoat the fact that a bit of effort is required to get everything working together. Again, it speaks to that practice element and understanding what works and what doesn't. And that was really done, that heavy lifting was done with what we did with our imaging effort. But once all those components were working, it ran smoothly, and the transition to doing exoplanet measurements was relatively straightforward and extremely exciting. So I am going to do some switching here. Okay, I'm going to bring up a couple screens here. Just going to do a little test, make sure something works. Okay, so we've got two programs up here. The one on the left is a planetarium program. As I said, everything works together, and which tells you where your scope is pointing if it's connected correctly. And the one on the right is the astrophotography tool we talked about, the hub of everything. Just trying to get things to work. So in terms of the astrophotography tool, you can see the screen here. So you've got a camera connection that if you had a camera, you'd hooked up to. I have a telescope, simulated telescope hooked up to the scope, which is simulating what we would do in real life. Here, I'll just maximize this for a second. So you've got also the ability to connect focuser, filter wheel, if you need a rotator, all to your setup. Okay, I'm trying to do something here. And it's not, of course it's not working because this is a live demonstration. That's kind of a natural law,
The way it always works.
isn't it? There we go. Okay. You saw the thing move. Okay, we're on Altair now. Let's just see if I go Control 1 on this planetarium program, it should now move back down to Deneb. And you'll see the corresponding change in the RA and the deck, those absolute coordinates in the up here in the planetarium program. And if you look at Deneb, yeah, we got 20, 41 and change, 45, 17. That matches. So they speak to each other. Now there's a lot of old time observers and imagers who I envy, who know the sky so well. The thought of a planetarium program is alien to them. I'm not that guy. I want and like a planetarium program to know where my scope is pointing and to make sense of things to me. And the technology that's available, we're using it. To me, it's fantastic. So we've got that ability to move the scope around automatically. And when it moves, it'll start tracking. And then we have the guiding going, which I'm not showing, but that keeps very stable on a target. Okay, I'm going to maximize the program here again for capturing the images, APT. And what I would like to do is show you. So this is an example image. This happens to be a 2-minute exposure, but it could be a few seconds for just targeting purposes. And what I'm going to talk about first is the plate solving method. Embedded in the APT program is something called PointGraft. It's its utility for doing plate solving, and that is linking to a program called ASTAP, which is kind of a revolutionary, relatively new plate solving program. What you can do with this is if you can put a scope position in and do a solve. And basically you're solving for where this is in the sky, what this image represents in terms of its location. Or you can do a blind solve. The scope position will leave in here. Actually, I've got a target. I've got to put in the correct target before I do that. So what we're going to do is we're going to move to a target. Sorry, I'm doing this in the wrong order. So plate solving allows you to do this. I'm going to just do this blind just to see if it works. This is extremely risky. Okay, that might not be good. What I want to do is show you the workflow though. So I'm going to get out of this. So I'm going to show you how this all works in relative terms after I've showed you how we get a target. Basically, I want to show you that we can move this telescope back and forth using either the APT program or the Stellarium Planetarium program. So to honor what we talked about in terms of the workflow, I'm going to take you to the Swarthmore College database. This is a small college in Pennsylvania that maintains an excellent database for exoplanet transit candidates. As you see, it contains NASA exoplanet archive, so established planets or strong candidates, and also the TESS objects of interest. Now, TESS stands for the Transiting Exoplanet Survey Satellite. You can see now there's over 5,800 of these candidates. Another database, and you can put a single object. This is a great, straightforward database to use if you're looking at trying to do some exoplanet work. You can put in your observatory coordinates, your lat long, your time zone, what day you want to look at. I've got one in history here, and there's a reason for that because that links into what we were talking about on the showing APT. You could show your elevation constraints that you want. If you've got some elevation constraints that you want to honor just to get good images, or just if there's things in your way, hour angles, another targeting parameter, and you put all those things in. And one of the important things is you want a a depth of a transit. The depth here relates to basically brightness reduction. So the higher parts per thousand, the higher the degree of brightness reduction there'll be of a planet crossing a star. Here, you divide this by 10 to get the percentage reduction. The magnitude, so we only want stars brighter than a certain magnitude, and you can put that in. If you put those things in and you hit submit, and I do this for the date that's relevant, which we'll show you in the example, it'll churn for a while, and then it'll spit out candidates for you, for your location. For that makes sense. Now I want to focus on this one. This is the one that's in the program we'll show you. This is TOI, TESS Object of Interest 4059. It's got this magnitude is 13. It shows you the moon phase at the time. This was in March. This is the start, middle, and end of the transit determined by the TESS site and maybe some other measurements. So this is a 2-hour transit, starts at just after 10 o'clock, ends just after midnight. And it's got suggested shoulder times when you should start imaging and you can finish imaging. And importantly, it's got an error associated with it. It has 0 errors. So essentially you can be anticipating the transit to start on time and finish on time. Again, 2 hours. Julian date, elevation, again, from where you are, that's kind of middle of the sky. It's not high, it's not low, it's doable. Skip over that for a sec. And azimuth. So basically you've got your 2 coordinates. So if you've got a constraint walking your way, you can tell if you can do this or not. Then you've got a transit cartoon, if you like, that shows you, what, in relative terms, what the depth is and what it'll look like. Again, that HA constraint we'll talk about. RA in a deck. This is critical. This gives you a very precise celestial coordinate in terms of the right ascension and the declination that you can actually take, cut, and paste into your targeting. And that's what I was doing out of order earlier, but I want to do it. So in APT, you can take those coordinates and you can add a new target and set those up. I happen to have that TOI 4059 in here, and I've entered them here, the RA and the deck. I hit OK, and that'll populate up here. If I bring, I'm going to minimize that, and I bring that into my program, and I hit go to, you can see the scope. This is moving faster than in real life, but the scope will move now to that target. So that's how simple it is to get an exoplanet target and to put it in a program and to move your scope. If you've got everything set up. Again, I'll just go on here just to show you where we're at. 1815, 7653, we got that target. Okay, I'm gonna maximize this again. Our scopes move to our target. What this represents, this picture represents that location of that target with a raw image. And again, it could be a few seconds long. This has to be 2 minutes. It doesn't matter. But when I wanted to show you earlier, and I did it out of order, I'll show you now, what the solving looks like on plate solving. Basically, you hit solve, and within 2 seconds, you've confirmed where you are pointing at in the sky. Now, this target right here is our target star. I could get it closer by putting in the object and doing something, which I won't do here, a so-called go to plus plus. Basically, what it will do is it'll move the scope a little bit, take another image, plate solve again, and then come back and try to refine the targeting. You can get that so that dot, that bullseye, is directly over the target star. But I just wanted to show you just basically what the plate solving function looks like. It's phenomenal technology, and it's mind-blowing when you first do it as an astrophotographer. But you can see how powerful it is. Okay, so the whole process here is, as we talked about, you get your target centered. Then you want to do your exposure control. So you'll take 30 second, 60 second, 2 minute, 3 minute images of your target star. But how do you determine if it's a suitable exposure? Well, if I zoom in on this image, that's my target star. I have something called pixel aid, which will determine. So if I take it to the background, now the absolute maximum scale here is 65,500. It's like everything's scaled to 16-bit full well depth Won't get into the details of that, but just that's the full scale representation. The background here is around 2000. And that's because there has to be a little bit of an offset for your camera to be good, so it doesn't, you make sure you're actually getting some photons in and not going below your black level. If I move this over over our target star, you can see it's still pretty faint, but I get up to a maximum pixel count of 5,500, and the maximum count on the count on the maximum pixel of location in there of 5,500. So whatever's in that frame, the pixel with the highest pixel count shows up as 5,500. Now you don't want any pixels to exceed 65,500. You don't want any pixels to exceed anything approaching that. And but you can see that you can do it. So basically you'll take different images and you find out what you can actually see. This is the low end. Normally we're in the 20,000, 30,000 range, but I wanted to try this and we did, and I'll show you the results in a bit. But we actually could, this is the one we're talking about, designing in the 5 or 10% range of the camera capability. But that gives you your calibration. With that knowledge, you set your exposure level, your tracking's going, your guiding's going. You basically can start an imaging sequence, which we'll just show you here. Basically, this is the exposure time in seconds. I bin my little 294. It's irrelevant, but that's what I do. And you put in a large enough count so it'll do the transit without a problem. And you manually stop it later. So you do that with the camera connected. I'd hit start and I'd start imaging. So images would start collecting in my folder. And that's all there is to it. If your guiding's working, your tracking's working, you set it and it works. And if your mount's good enough, you don't have to worry about that anymore. Okay, back to the presentation for just a sec. No, I want to show you AstroImage J. Okay, so we talked about processing. And this is the AstroImage J program. I'm going to restart. So basically, if you've got images coming in, what I've done is I've loaded all the images from a recent one I've done with the target star centered in the frame. And you can see that there are 67 images. These happen to be 3-minute exposures. Doesn't matter. It's just for illustrative purposes. But I want to give you an idea of what the workflow is for AstroImage J in post-processing. And in real time, it's similar. It's just that you have to wait every 3 minutes to get a new data point, or 2 minutes, whatever your exposure level is. If I zoom in, and I know this is my target star because it's centered in the frame, and we hit Alt, you can actually determine, you can see there, what it does is give you a suggested radius for what you need to surround the star with to contain all its bright pixels, then that buffer zone, and then that outer radius for reference zone. And it'll give you that from just clicking on that target star. If your star bloats and you can see how it steps as I go, I'm stepping now up in time. It kind of changes a little bit due to atmospheric conditions, and you play with that a little bit. And if you got good seeing conditions, that aperture won't change. Anyway, that gives you kind of your initial aperture. The sweep away function, get rid of that one. So in terms of actually doing the photometry work, it's really quite straightforward once you've got a good stable series of images. Basically, you hit your photometry button, you want to place apertures, you place it relatively near the star with a left click. Then the later versions of the program do this to their varying degrees of success, but they give you a pile of reference stars that should work. They don't work very perfectly, so you got to do a little vetting. But I'm just going to go ahead and show you what it looks like when you right click and you start basically generating in a post-processing way a transit. So you'll see in the plot here, we're adding data points as it's processing. Now the processing is taking away flats and darks and biases that we've already put in there and set up as you do for imaging. I won't get into that. Basically, they're calibration frames that allow you to take away any artifacts of the camera as much as possible to allow the pure image to come through. So you can see here, the thing below is a reference star. I just plotted one here, and here's the transit. I just did this one at the end of August. I haven't really processed it very much. This is a new TESS object of interest. You can see it's 5,259, but you can see that it's got a very shallow depth, but we've seen a transit here. You can see it looks subtle. There's a bit of noise, and there it is. One of the things you can do with the edge, you can actually show errors if you like. Yeah, I'll plot that up. Auto error, and the auto errors not that bad. You can model. You can show a model of the. Obviously, this is a little earlier than what the TESS has predicted. A little bit, both on the ingress of the planet and the egress. Now the modeling is allowed if you got good enough quality data. We'll talk about that a bit later. But you can actually set up a model and determine some parameters from that. Anyway, that's a transit. That's exciting to some, boring to others, but we find it extremely exciting. It represents a planet crossing the face of a star 300 or 400 light years away that we detect on our own. Okay, what do I do now? I'm going to go back to the presentation. Anyway, I briefly wanted to, there's a lot to that, but I wanted to show you a bit of the workflow. Okay, so what can you do with the measurements you make as an amateur? Going back to the known planets, obviously you can make your plot like we just showed, and you can stick it on the fridge and admire it, which is great. And you can share your joy and maybe inspire others to look up, and that's no small thing. But another is to make measurements of known exoplanets, both to kind of refine your technique, maybe add a little bit to science, but extend your knowledge of things. But it also can add to some science. This is a Czech database, Exoplanet Transit database, and it's a good one. And this is a transit measurement we did very early on of a known exoplanet called HAT P4b. And this plot is of an orbital deviation. So this thing was discovered in 2007, and you can see there's a deviation trend that goes down here, and that's observed minus calculated orbit, orbital parameters that basically has changed over time over those last 15 years. Now, a paper was written on this because I was interested in how this all worked. That predates our data, so it was already established. That showed the reason for the deviation was the existence and orbital orientation of a second planetary system, second planet in the system. So there's a companion here to go with the other one, and that's what was causing these deviations. But a paper was written on that. So this is an example of confirming some established science along with just confirming your technique, which I thought was kind of neat early on when we were doing this. Now, here's a measurement of a planet candidate. This is a very deep one. That's why I'm showing it. You can see how dramatic it is, a 5 or 6% depth. There's no mistaking this one. And you see the dip and the brightness coming back as the planet finishes crossing. And the reference star brightnesses are stable throughout. Sorry. For the enthusiasts in the audience, imagine you're looking at these data you've generated as an amateur. It's only a graph again, but it represents that distant planet. And if you do it in real time, the thrill is that much greater. Okay, here's another example of another product of submitting data to known exoplanet databases. This transit is one we did in March of 2021, and it was interrupted by clouds. You can see the break here. But only briefly and luckily near the well of the transit. The start and the end times were quite well defined. And I submitted these to the TESS ExoFop database. I was lucky enough to obtain login and submission privileges for the MIT Harvard database. And the exciting thing about this one, the data were used in a new peer-reviewed paper, published paper. And it's a study, an MIT-led study that determines there's a population of planets in binary systems whose orbits are aligned with those of the binary system, how that binary system rotates or revolves around, the stars revolve around each other. Now, TESS data submissions of sufficient quality allow inclusion in such works. And Sam Christian here, I think he's now of MIT, included us as a co-author because he used our data. Moving on, again, we talked about the Transiting Exoplanet Survey Satellite TESS. It shows here, now this is over 5,800. This is taken a few weeks ago. There's that many candidates. It says only solid confirmation of 221. The bar is pretty high to confirm planets, so more data is needed and much more work to confirm them. And really, professional astronomers and large observatories can only do so much in terms of basic transit timings and calculations. So, and also these professionals, as we know now, like when we look at James Webb, they're looking for exploring more details about exoplanets and looking for habitable ones, rocky habitable zones, including things like looking for topography with light changes, which is incredible, and atmospheric composition, things that their equipment can contribute to, and it's exciting stuff. I think amateurs, though, could contribute a lot to the bread and butter data collection to help fill out some detail in the data leading to more confirmation of exoplanets. That's what I've basically tried to outline a bit here. So far, we've done 12 submissions, and some with already lots of data leading to planet confirmation, and our data supplement. And that's a useful exercise contributing to science, I think. Recently, though, more and more candidates have been revealed. The initial TESS sweep of the sky, or the couple sweeps, revealed target star candidates of about 10.5 magnitude and brighter. The faint star effort expanded that down to about 13.5 magnitude, roughly. Now, because of the sensitivity of our camera setups, which I tried to illustrate a little bit, even with a limited, again, citizen-type telescope aperture, we've been able to do exoplanets down to mid-12s magnitude. And again, Jim, just to take an aside, if you've got a Meade 16, you're going to be able to see, and any camera like this, you're going to be able to see some very faint candidates.
Cool.
So this has allowed us to try some candidates for which there's no other published data beyond the initial identification of a candidate by the TESS spacecraft. And we think it's cool to maybe be the first to help confirm a new planet with Earth-based measurement. This is one such planetary candidate, TOI 4103. We did it last November, and it appeared to be the first time series transit in the TESS follow-up database. And there's been a few more transits of 4103. And just indulge me, I want to show you the Exophot database. So basically, I've got login privileges here. You do it. I don't even know if you have to have login privileges to do this. So you put in the TOI name and you hit enter, and you'll get a so-called tick search result. And up will pop what data are available for that candidate. Busy screen. I just want to focus on down here on the time series observation. So this is us here. We did it in November of 2021. And at that time, there were no other transits listed. There's since been follow-ups by professional astronomers in April, May, and June of this year. But it looks like we were the first to put in the transit from Earth. And yeah, we want to just show you, if you download that, you can get it up on your screen. Yeah, that's our data in there. Anyway, being first, it's kind of cool. It's not necessarily that important if you're contributing to science, but it just shows you what amateurs can do, potentially.
Well, if you imagine how many exoplanets are out there, I mean, that seems like something that amateurs can help with.
Absolutely, and that's the exciting thing with all these new candidates. I don't know how the heck the professional astronomers will keep up. Again, this is one we just did earlier. This is another first one, I think, 5588, And I've just, and here you can see the modeling results on this one. Again, these model results are highly dependent on the quality of the data. But as an estimate, if you put in the period of the planetary orbit around its star, which you get from other methods, including the TESS data, and you put in the relative radius of the star, again, obtained from other measurements with respect to the sun, and you get a decent enough transit, you can get things like its orbit size. Here it's showing it's about 40% of the Earth's sun orbital distance for that planet. But the planet itself is a super Jupiter. Again, the one we did that there weren't any other data for. Anyway, so the modeling's based on knowing orbital period and distance, that kind of thing. But we think that's pretty exciting and just a demonstration of what potential amateurs can do. Okay, really, that's it for the exoplanet. Been a little bit vague about our geography location. What we've done, as we talked about, we made a move. And I've just put a light pollution map up from relatively recent. This is our situation in Calgary, in suburban Calgary. And we were right in the middle of this Bortle 8, Bortle 9 mess. And we've now moved to 7 persons. So here's the Rocky Mountains here. There's Calgary. There's the Montana border. There's the Saskatchewan border. We moved all the way down to the southeast part of the province, just offsetting a little hamlet called 7 Persons. It's basically a rural area with just a hamlet nearby and much darker skies. Now you'll see what I say here, art and science, no conflicts. So Kimberly needs her images and I want to do more science. We both do. But so we've basically constructed in the final stages of construction of a new 3-pier observatory with a roll-off roof.
Ooh, that looks cool.
And
I want one of those, Mark.
Yeah.
so there's the roof rolled off. There's a 16 by 16 warm room in here, which will show, and this is a 14 by 20 observatory. This is early on in construction, so there's 3 piers here. Superstructures are going on these metal superstructures to hold the mounts. Hold the mounts very close to the wall height.
Yeah, gotta get me one of them.
And there's just one example. We've just got a prototype extension structure with our 140 and the Mesu mount there. So we're fairly excited about being able to do our hobby in a much more intense way here. There's
That
the warm
extension
room.
structure, does that go like up and down, like whenever you open
Yeah,
up?
this one's a little too light for this mount, but yeah, there's basically it's square tubing with smaller square tubing that can go in and out, and they've got basically 3/4 ready rod here to allow for height adjustments to move those up and down.
Wow,
The
that's
square
cool.
tubing is for torsional rigidity, and the 3/4 ready rod's really for up and down rigidity, vertical rigidity. This is a warm room, still got cement floor. We got to put flooring in, but this is just as it sits kind of today, testing things out. All the cable pass-throughs you can see here, we've tested out. So there's no cables. Yeah, and we're excited about that. And that's where we're at. And on that note, Kimberly, you can conclude by saying thanks as well, but I want to thank you people for listening and for being interested in what we're doing. And if I can help or we can help with anybody, please get contact deals from Jim, both in imaging and some of this exoplanet work. We'd be more than glad to. It's a rewarding activity, imaging and doing this, and it's we think it's got the added benefit of contributing to some science.
Well, we're already excited because one of the cameras we were looking at funding for the observatory is the 294. So
yeah, it's a good camera, and it's less expensive than 2600, but you don't need a wide field for this, right? You think about it, you don't need a very wide field if you're doing exoplanet measurements. If you're doing imaging, I don't think the 2600 is just a cat's ass for a camera. It's just beautiful. It's the right size. Kimberly loves the images that are coming out of it.
Laurie, there is one question there about have we tested other cameras? So maybe you can speak to the couple other ones that we have tested.
Yeah, does that mean? Do they mean from
I
an
think it's
exoplanet perspective?
Well, the ZWO cameras that we've tried,
Yeah,
4 different ones.
We use the 2600, Well, actually, we started with the 1600, which is kind of an earlier generation of the cooled mono camera, and it worked fine. It's a noisier camera, we did the 2600, which is, I think it's an incredible camera, but it seemed like overkill for exoplanet work, so we bought the 294 to free up one of the 2600s. We've got two. We've got, for imaging setups, we've got a 94 millimeter refractor now, as well as the 140. I don't know what we'll do in the future. The call to do something longer focal length will happen, but we're going to test out these with the good camera. And the Schmidt Cassegrain is not ideal for imaging for a variety of reasons. It's you can get small planetaries with it and do planet work. But that's my primary our primary exoplanet scope, and we're using that with a smaller mount, even a Rainbow Astro RST 135, which with that long focal length it works incredibly well. But yeah, we've tested the 2600 and the 1600, and now we're just using the 294 for practical reasons. But the 2600 is a camera that can do everything.
We had another question on here. Imagine seeing and transparency of the night has to be super. Do you check that before you start your session for minimum clarity, seeing, etc.?
Obviously, the seeing and the transparency, the better it is. But because of the method of the calculation, and especially for a deeper transit or a known planet, you can get away with less than absolutely ideal sky conditions, because you're basically doing a comparison. That relative flux, comparing it to other comparison stars, and you can play with those and find out if you're really getting a unique measurement or not. So you can get away with a little bit. In terms of quantifying it, I'd be loath to do that. I haven't done that extensive. We tend to only go out when it's nice and clear and do things, because that's what we do for imaging. But I haven't tested the limits of exoplanet measurements for less than ideal skies.
How many clear nights a year do you guys get? About?
Way more in our new location. It's one of the sunniest places in Canada.
Okay.
I don't know, Kimberly, what do you think?
I think we had a bad run this winter. We had a lot of cloudy nights and a lot of clear skies when it was full moon, which doesn't help. The summer was pretty good though. We had a lot of clear skies, so I'm hoping our fall and winter is better this year.
Cool.
Have you discovered anything that's worth naming?
Sorry, didn't hear that. Discovered anything that's worth
Naming in the skies, like an asteroid, comet?
Oh, in terms of a raw discovery?
Yeah.
Not to date. We've mostly falling, and people, I get asked that a lot. Like, don't you want to just point your camera, for example, at a star and hope for an exoplanet?
No.
I don't have that kind of time.
Yeah.
You know, they put this spacecraft up there to hunt out these candidates, and they're doing such a great job of it that, you know, if you want the glory, well, my glory, you can see I'm a little bit of a glory hunter, and that I want to be first on Earth to do something that the TESS spacecraft might have kicked out. But that's kind of where the limit goes. You know, people ask that all the time. Like, do you want to just find one that nobody's ever even seen before? Yeah, sure, but where do you start? That's what they did this spacecraft for.
Go ahead, Rick.
How do you distinguish between a normal variability star, maybe even a smaller star versus a planet, like a small white hole? How do you distinguish them?
I could only hear a bit of it. It was like, how do you tell it's not a variable star versus an exoplanet?
Rick, the mic's over here.
Okay, well, obviously, I'll keep on. How do you distinguish it from a variable star? Like I said, yeah, it's normal star variability, and it stays not a planet, say it's like a small, like a black star. How do you distinguish?
Yeah, I gone into a little bit of that, but mainly I'm looking at these candidates that they pre-filtered for that now from TESS. But it's a valid question, and you know, obviously people are looking into that. I haven't done a ton of that in terms of eliminating those variables. I'm relying on the filtering, candidate filtering.
Yeah, the website from TESS does all that for you. You basically select the star you want, and it gives you the times for the transit.
Yeah.
Otherwise you'd be out there all day or all month or whatever, trying to get the transit.
Or lifetime.
Yeah,
I have a question.
go ahead.
The top of your graph shows the dip, but the bottom half shows 3 bars of several colors with no dip, but just variation. What significance do those 3 bars have to the top bar with the dip?
Those, and the one I showed you with the really flat ones is just a really good example of reference stars not changing in their brightness.
Oh, they're reference stars.
Yeah, sorry if I went over that too quickly. That's my fault.
Oh, I asked you, I would never figured it out.
No, I'm sorry. Like, so the reference star in that particular example, and on the other one, I just showed one and some of its variability. But those are the just an illustration of the reference star brightness not changing. And the reference star brightnesses can change. It's just, you know, that was a great example of them not changing and being flat compared to the target star where the planet was.
So in other words, that's what software uses to help understand the brightness of the main star you're monitoring, right?
Exactly. Yeah, it's just a calibrated so-called flux reduction that uses all of that information. And really, when you look at it, it's just algebra.
Go ahead, Rick.
One more thing, it seems so intimidating to an average person. How does someone who's never done this, how do you get started? Is there a primer somewhere, or you just ask somebody like you, or, you know, like it's a million steps, you know?
I was hoping for the exact opposite effect, that you wouldn't be intimidated. Like we started this 5 years ago, and yeah, I'm a technical person. Kimberly's more of an artist, but she's not technically bad either. She's pretty bright with that. And it was really from a perspective of wanting to get good images and what you need to do that. And it's coming from the exact opposite side that a lot of people do. A lot of people want to start with the science, do variable stars, and that's great. I'm just trying to illustrate that this isn't the only way. It's our way, and what we happen to develop in terms of skills and using equipment and having the ability to do that, and the time, is I basically got a lot more free time than Kimberly. Is dive into it and practice, but from the imaging side, all that precision and that work allows you to do this. But it really shouldn't be intimidating to anybody that's technical, that has the passion for it. My whole thing in this is persistence is way more important than patience in this endeavor for imaging and doing this. So
See
we'll
the
get a little mad, but
146.5 sharp star can see up to 13th magnitude. Is that
Yeah.
the limit?
well, I don't know. Yeah, that's kind of the limit we've seen. You see that really low count I had there? That was like a 13 magnitude star. Really, I think that's pretty close to the limit of what you can do with that aperture.
Okay. Go ahead, Grant.
Yeah, in one of your earlier images, you had what looked like a mini tent over your laptop.
Yeah.
Where'd you get that? What is that?
I don't know. We got it from a.
Grant's kind of into gadgets.
Here, I'll try.
Yeah, I
to
noticed that too. That looked interesting.
You mean the red in the image that was all red?
A little igloo for your computer.
Yeah, I'll try to bring it up again.
When you take your hamster camping.
It was an outdoor shot. I think it was.
It sounds like a really smart little way to keep the light from your computer to
Hey,
disturbing
Grant.
everybody.
Mark
We
Jones
did
said-
buy those for 2 reasons.
You're
The
talking about
first
this
reason,
thing?
yes.
Yeah, there you go.
Yeah. So we bought those for 2 reasons. Number one was we were sitting around with a bunch of observers, so they are very hesitant to have light anywhere. So that really helps. The second thing those really help with is when you're in these colder climates, it keeps the laptop from frosting up. It keeps a little bit of heat in there. So they're really great.
That's right. And down south where we're at, it keeps the humidity off. It keeps the
Yeah.
Yeah.
yeah, because I do astrophotography, and one of the things I've got is I've got a kind of a homemade thing to put over my laptop. And also I do a lot of solar work. So that looks like that could be dark during the day when the
Yeah.
sun.
That's what we use it. We use it too for we've got a cork chromosphere, and we use it for that in the daylight. But a lot of people just use utility buckets, plastic utility buckets turned on their side.
Or box.
Yeah, it's
Well, yeah, I got a box, but that thing looks like that folds up really nicely.
It does. It can be a bit of a pain in the ass in the middle of the night to zip up and everything, but it actually doubles as a carrying case. Like if you're packing up at night.
Yeah.
Which now that we're having our observatory, hopefully those days are mostly behind me. packing stuff up like wiring that you don't want to leave out, all that kind of stuff. You roll up and you throw in there after you've closed your laptop, and it works.
I know you spend hours getting all packed up real nice and neat, got your checklist all checked off, and you get home in the morning, you get this jumble of stuff.
Yeah, and like
So
you
what
say,
else-
if you've got humidity, it can be wet and mucky and all
So
sorts
where
of stuff.
did you get that? Do you remember?
Oh God.
I do. We got it from a personal friend. I'm just looking on the net here to see if we can find them
Yeah,
for you.
you look it up, and maybe I can deal with another question while you're doing that. I got a question. Why are you using that 140 millimeter over the edge 8 for your work? Really, we started with 140 because that was a setup that was set up in our yard. I thought, okay, let's try it because I've got this 2600 and the 140, and that's the first ones that we did that worked. Now I'm using the edge 8 because we don't use it for imaging much, and the 294. And you've got an edge 11, damn right that would work. It would work great. As long as it's collimated. And again, there's issues with Smish Cassegrains for imaging, and I won't get into that, whatever, but there's a limitation on them. But for exoplanet work, where all you're trying to do is contain all of the brightness there in whatever star form you can, it worked great. I don't know why I can't get this pane to be open. Okay. Tested other cameras. Suggested reading, Kimberly, for nightscapes.
Oh, good question. Well, let me take a look at my books. I've got a couple of really great ones. I just can't remember. One of the best ones I would say is probably Alan Dyer's book on the backyard astronomer. He goes through all the gear that you need, and he goes through if you want to do wide fields, or if you want to do tracked, or if you want to get into the deep sky. It's a really great beginner's guide. I'll put that one in the chat too. I just put the tent in there.
Guess who our December speaker is?
Alan Dyer.
Yeah.
Great. Okay. Well, listen to him. He'll tell you what to do for wide.
He's an awesome speaker, and he's a good friend of ours.
Yeah.
And he's been nothing but supportive of what we've been doing, both for imaging and this exoplanet work. He's been a great mentor in the past and a real good supporter. He's a great person.
Yeah, just so you guys know, they sent me the link for the laptop tent sunshade.
Yeah,
There you go.
that's pretty bloody pricey for one of those.
That's
isn't
the
it?
Canadian version, so it'll be cheaper in the US.
Yeah,
Funny
by
money
about
version.
$5. Hey,
Well, if you started to count shipping, though, that would matter.
ooh,
Shipping from Canada is not pretty.
Right.
Yeah, I think ours were 80 or 90 bucks Canadian at the time.
They
weren't
were. They were. Yeah, and we've had them for 4 or 5 years.
holy cow.
Yeah, go ahead, Rick.
Hey, is there any value to actually images? I can see the exoplanet work, but do professionals use those images, or is that just for fun? Is there any useful work to do editing those kind of images, other than say finding a supernova or something?
I'm sorry, I can hardly hear that. Sorry.
Taking the actual images, is there any actual value to the images, other than for say like finding a supernova, or is that just all for fun? Do professionals use those images? You take it all, or the processing you do? Is there any value to that for science or for fun?
In other words, do your images get used by scientists?
Yeah, and we just showed an example of it. That published paper, the MIT paper, you're included as a co-author. They included all the data for it. Again, if I went over that too fast, I apologize.
Yeah, what do they do?
Here, I'll get this one up.
He wants to know what they do with it.
What do they do with it? They write papers and look really intelligent. And they determine possible alignments between orbits of planetary system and their visual binary companions, which I think is a very worthwhile exercise. I think it's incredible. We can just contribute a little bit to this with, just confirming some ephemeris or whatever, and some timings of transits.
And I think the more confirmations they get from amateurs validating their targets, they'll turn James Webb that way and take a look and see if they can find the composition of those planets now and see if there is actually life. So you're contributing to science, maybe in a small way, but if it all adds up and it gets to James Webb and they do find an inhabitable planet, then that's huge.
I'm thinking more about the pictures themselves from Dave, the pictures of the nebula and stuff. That's what.
Oh, the nebulas.
I thought, is there a value in this? You've already got this by professional skills. That's why I'm asking. The amateur pictures, are they useful? Anyway, I was asking.
I don't know. I don't think they're using science. In fact, there's a big debate about the people, like if you look on some of these websites, they look down at pretty pictures. We don't have that opinion. We think they're cool. They're art for its own sake, but it's, you know, depicting something otherworldly that's outside of us. It takes us away from this this dirty ball of insanity that we live on sometimes. I don't know. I don't know if that answers from my perspective. I don't know. I got a question here about the ZW294. It does suffer from amp glow on the one side. And I glossed over, I went too quickly, but basically we use calibration frames to eliminate those. That is one great advantage of the 2600. It doesn't have any of that amp glow. But the 294, it's a less expensive camera, smaller chip, that kind of an earlier generation sort of that does suffer a little bit from amp glow, but that was calibrated out very well with application of flats and darks. I don't know. Somebody asking a question. I can't hear anything.
Oh, yeah.
I had a question, if you can hear me. You showed one of your data sets where clouds came in and interrupted the data collection for both your comparison stars and for your target star.
Yep.
Have you had cases where you've where during the course of the observation that the skies have deteriorated or seeing has deteriorated to the point where you have to use other software tools to curve fit?
If it deteriorates a little bit, you can overcome that. It just, the data can look noisier, but often you just have to terminate if the sky deteriorates too much. And one of the ones, I don't know, I have it at the end of the transit, dawn was breaking, and that just causes haywire in your data definition. No matter what, obviously, you're getting some light. But stuff like that.
You can take your raw data and you can change the size of the annulus afterwards, right? And pre-process your data.
Yeah, there's a lot of things you can do, and I hardly even touched on it with Astro Image J. You can invoke a variable radius. So say your focus changed, and you can do that. There's a whole variety of options that I've only scratched the surface on for some of these. The beauty of having good equipment and keeping stable images and focus is you don't have to take advantage of that as much, but they're available. And I can see why, you know, the previous equipment might have dictated that early on. And but all the image stabilization routines are in there. All of that kind of stuff is available.
You mentioned hour angle as an important parameter. Do you need that for when you're doing mirror or pole swap on your on your guiding?
Doing what? Sorry, fault.
When you transit the meridian, or when you may have to do a pole swap when your German equatorial has to swap from one side to the other. You want to avoid that, right?
Yeah, you definitely want to avoid that, but you can overcome it by flipping images post-processing. Real time, it's a pain in the ass. You can't really do much, but or you can actually flip them and then restart your real time if you want. But yeah, those are things. But the capture program we keep an eye on, and you know, I don't really trust automatic meridian flips, so I always do it manually. Keep an eye on where I am with both for imaging and for the exoplanet work. And I've never looked at the hour angle specifically for that. We just get this automatic readout how close you are to a meridian flip being required for your mount.
Any other questions, guys? Anybody from Zoom? Well, man, this has been awesome.
Yeah. Very good.
I knew our group would like it. And it's especially appropriate since we just decided to start working on putting together a camera and stuff for our observatory. So we're looking forward to that.
Yeah, it's exciting. Exciting stuff. No, we're really appreciative of being able to talk to you people. We appreciate the turnout and the interest. And
yeah, I think we had about 40 people altogether, 45 maybe.
yeah, that's exciting.
I know we had 30 online.
Yeah.
Plus there's a little more than a dozen down here live and in person.
Again, serious about the invitation. If anybody needs any advice or help, either through Jim or you can talk to or whatever, just be more than.
Yeah, if we get around to doing exoplanets at the observatory, we'll definitely check it out.
Yeah.
Thank you, Laurie. Thank you, Kimberly. Beautiful pictures and very interesting talk. Thank you.
Thank you.
Thank you very
Excellent.
much for having us.
You guys take care.
Okay.
We'll do. We got some. Do we have your address?
Let's pop.
Email your address to Bradley.
Okay.
Because he's got something he's got to send you. Mailing address.
Mailing address. Okay.
Yeah.
You bet. We'll do that.
If you want the PO, and I don't think I can mail international with PO. You have a regular address?
We do. Yes.
Yeah, we do.
Cool.
I'll email that to you. You bet.
Real quick. So you talked about moving near a hamlet.
Yeah.
What's the rough size? How much is the population of a hamlet?
Well, the title of the name of the place is called Seven Persons.
Yeah, and then you mentioned
That's a joke. There's a couple of different fables. I don't know which one's accurate. But all of them involve 7 people dying. But it doesn't matter. But back in history, obviously. But no, the hamlet, I don't know. There's probably 50-ish dwellings.
Yeah. It's less than 100 people, probably.
Okay, cool. Yeah, because I'm not used to the term hamlet, town, city,
Yeah.
Get kind of a general idea how big that is, but a hamlet?
Yeah, and no, and I don't know where hamlet turns into village or town or whatever the designation is, but yeah, it's.
Well, it says fewer. Google says fewer than 100 is a hamlet. So.
Okay.
Shoot, I should have thought about that.
Yeah, it's a nice little place. Its claim to fame is a great sausage shop where they.
Oh, there you go.
Stuff.
Hey, you guys are cordially invited to stick around for a bit if you want. I've got what they call an A101 presentation on spectroscopy.
Wow.
But if you want to bail, you can. But leave it totally up to you.
We'll hang around. I just need a refresh on my beverage.
Yeah.
Great. Thank you again.
I got my refresh.
Awesome. No, we appreciate that. We'll hang around. Yeah, that's great.
Thank you.
Yeah, go for it. I just emptied my bottle.
Good. Again, thanks you guys. We really appreciate the interest. And
No problem, Laurie. Thank you very much. Appreciate it. Glad I went to that conference. I'm telling you.
it's awesome. Well, one more question. Who's the third speaker? You got Alan Dyer.
Alan Dyer. Oh shoot. Natalie, I forget her last name. She's the JWSC representative from Canada.
Okay, cool.
She's coming up next month.
Oh, she was good. Yeah. Okay.
Yeah. So you can, if you want to talk to her, see her again, you're welcome to join us next month.
Well, yeah. If you could shoot us links to those, that'd be great. If we can, if you're.
Well, it's the same. It'll be the same Zoom link.
Okay. Perfect. That's great. Just need the time. I'll look in.
That makes it easy.
Perfect. Thank you.
All right.